Hello friends, in the previous video we showed you how to solve a 2D transient heat conduction problem in Cartesian coordinates using forward time centered space finite difference method. In this video we are going to solve the same problem using backward time centered space or BTCS finite difference method. Our objectives are to present a simple 2D transient heat conduction problem with no heat generation. We will then discretize the domain into, say, a 4x4 grid. We will consider two time steps and solve the problem using backward time centered space or BTCS finite difference method. We will then vary grid spacings and time steps and resolve the problem and obtain temperatures inside the domain. Our domain is a copper plate which is 1 meter long and 1 meter wide. The material property called alpha equals 1 e to the negative 4 meters squared per second. Alpha is called the thermal diffusivity. The initial temperature of the copper plate is represented by Tn, which is equals 200 degrees Celsius. At time t greater than or equal to 0, all the four sides of the copper plate are maintained at 100 degrees Celsius. The x and y directions are shown on the left hand side of the sketch. The general heat conduction equation in 3D Cartesian coordinates is given as dou square t by dou x square plus dou square t by dou y square plus dou square t by dou z square plus g over k equals 1 over alpha times dou t over dou t, where the uppercase t represents the temperature in the domain and is a function of the spatial coordinates x, y, z and t, where the lowercase t represents the time in seconds. Alpha is the material property called thermal diffusivity and is given in meters square per second. Alpha equals k over rho c, where k is the thermal conductivity of the material in watts per meter Kelvin, rho is the density of the material in kilograms per meter cube, c is the specific heat capacity of the material in joules per kilogram Kelvin, and g is the volumetric rate of internal heat generation in watts per meter cube. We assume that the material thermal conductivity is homogeneous and isotropic in the medium. Accordingly, the thermal conductivity K is considered uniform in the domain. For 2D transient heat conduction with no heat generation, equation 1 reduces to a simpler form. We will assume that the temperature does not vary significantly along the z direction when compared with x and y directions. Also, since there is no heat generation, G equals 0. We then get dou square t over dou x square plus dou square t over dou y square equals 1 over alpha times root dou t over dou t, and t is a function of x, y and t. Rearranging this equation, dou t over dou t equals alpha times dou square t by dou x square plus dou square t by dou y square. T is a function of x, y and t. T is greater than or equal to 0. The initial condition is given as t at x, y, t equals 0 equals t in. The four boundary conditions are given as t at x, y equals 0, t equals t1, t at x equals L, y, t equals t2, t at x, y equals w, t equals t3, and t at x equals 0, y, t equals t4. Here length of the domain in x direction is given by L, and W represents the length of the domain in y direction. To obtain temperatures in the domain, we need to solve the above PDE. We will utilize finite difference method to solve the above PDE. To do so, we need to replace the partial derivatives with finite difference approximations. We will replace the time derivative with first order backward difference and the space derivatives with second order centered difference approximations. Accordingly, we get ti comma j n plus 1 minus ti comma j n over delta t equals alpha times ti minus 1 comma j n plus 1 minus 2 times ti comma j n plus 1 plus ti plus 1 comma j n plus 1 by delta x square plus ti comma j minus 1 n plus 1 minus 2 times ti comma j n plus 1 plus ti comma j plus 1 n plus 1 by delta y square. For simplicity, let delta x equals delta y. Also let the diffusion number d equals alpha times delta t by delta x square. By rearranging this equation, we then get equation 5, which is shown as minus d times t minus 1 comma j n plus 1 minus d times t plus 1 comma j n plus 1 plus 1 plus 4d times t comma j n plus 1 minus d times t comma j minus 1 n plus 1 minus d times t comma j plus 1 n plus 1 equals t comma j n. Equation 5 is the finite difference approximation of the original partial differential equation we were trying to solve. Here I represents the node location along the x direction, j represents the node location along the y direction, and n represents the time step. The above approximation is called backward time center space or BTCS method. This is an implicit method. Hence temperatures Tij's at future times n plus 1 need to be obtained based on Tij's at present times as shown in equation 5. Also, equations need to be solved simultaneously as we have unknown temperatures at neighboring points for the same time step. The advantage being implicit methods are unconditionally stable, but the diffusion number d and time step delta t still need to be smaller for accuracy considerations and not stability considerations in general. The truncation error of the BTCS method is of the order of delta t plus the order of delta x square plus of the order of delta y square. Now let us discretize the 2D domain into a 4x4 grid equally spaced as shown below. Here T1, T2, T3 and T4 represents the temperatures at the 4 sides of the copper plate, and Tn represents the initial temperature. We have 25 nodes in general. Temperatures are fixed at the boundary nodes as shown. Our interest is on the 9 interior nodes from 2,2 to 4,4. Let us apply equation 5 on the 9 interior nodes. We then get for node I equals 2 and j equals 2 minus d times t 1,2 n plus 1 minus d times t 3,2 n plus 1 plus 1 plus 4 d times t 2,2 n plus 1 minus d times t 2,1 n plus 1 minus d times t 2,3 n plus 1 equals t 2,2 n. Likewise, we can get equations for the other nodes as shown here. We will now rearrange these equations by moving the boundary conditions to the right hand side. Accordingly, we get minus d times t 3,2 n plus 1 plus 1 plus 4d times t 2,2 n plus 1 minus d times t 2,3 n plus 1 equals t 2,2 n plus d times t 1,2 n plus 1 plus t 2,1 n plus 1 for node I equals 2 and j equals 2. Here t 1,2 n plus 1 and t 2,1 n plus 1 are the boundary conditions and they remain same for all time steps. Let 1 plus 4d times beta equals beta. Rearranging the above set of equations into a matrix form, we get the following set of equations as shown here, arranged in a matrix form. The matrix shown above is a pentadiagonal matrix. Iterative methods such as Gauss-Seidel successive over relaxation can be used to solve the above set of equations. Let delta t equals 100 seconds. Note we have chosen a higher value for illustration purposes only. For accuracy purposes, you need to use a smaller value of delta t. Delta x equals L over nx, which is equals 1 over 4 equals 0.25 meters. Also, delta y equals delta x, which is equal to 0.25 meters. The diffusion number d equals alpha times delta t by delta x square, which equals 1 times 10 to the negative 4 times 100 divided by 0.25 square, which is equal to 0.16. Please note that the stability criteria need not be met for the diffusion number, since the method we are using is an implicit method. Let beta equals 1 plus 4d, which is equal to 1 plus 4 times 0.16 is equals 1.64. We will now substitute the values of d, beta, the initial and previous time step, and boundary conditions into the above set of equations. We then get the equations arranged in a matrix form as shown here. We can then solve the above set of equations using one of the methods, such as SOR. Solving the above method using SOR method on MATLAB produces the following results at time t equals 100 seconds. The temperatures at the various interior nodes are shown here. Likewise, for the next time step n equals 1, we get the set of equations arranged in a matrix form, which can again be solved using methods such as SOR method. We solve the above method using SOR method on MATLAB, and we get the following results at time equals 200 seconds. The temperatures at the 9 interior nodes are now shown here. Likewise, you can find the temperatures at these interior nodes at the next time step by choosing n equals 2 and so on. Graphical results are presented using MATLAB for this case. Using MATLAB or other software, we can develop codes for a general case where the number of grid spacings and time steps can be altered as desired, and solutions obtained accordingly. We will now go back to MATLAB. Here, the material property thermal diffusivity alpha equals 1 e to the negative 4. The total time is set as 200 seconds. The number of time steps nt equals 2. Accordingly, the time step delta t equals t over nt, which is equal to 100 seconds. The x length and the y length, which represents the dimensions of the copper plate, is shown here as 1 meter. The number of spatial grids along the x direction is 4, and since nx equals ny, we keep the number of spatial grids the same along the y direction as well. Delta x equals x length over nx, which equals 1 over 4 equals 0.25, which is the grid spacing in the x direction. The grid spacing along the y direction is the same. The initial temperatures shown here as T1, T2, T3 and T4 they are the boundary temperatures at the 4 sides, shown as T1, T2, T3 and T4, and temperatures are maintained at 100 degrees Celsius. The initial temperature is shown by T5 and is shown as 200 degrees Celsius. We'll now run our MATLAB program. So the diffusion number for reference purposes or accuracy purposes we get as 0.16, which is lesser than 0.25. The right hand side vector called the B vector is shown here. The pentadiagonal matrix called the A matrix is shown here. The initial temperatures at the 9 interior nodes are shown here as 200 degrees Celsius. The temperatures at these 9 interior nodes when time equals 100 seconds are shown again here. And the temperatures of these 9 interior nodes at time equals 200 seconds is shown here. We'll now look at the graphics side of the MATLAB. The temperature at the initial condition is shown on the top left hand side. For all the interior nodes, the temperature remains the same at 200 degrees Celsius. At the final condition, when time equals 200 seconds, the temperature profile is shown for the 9 interior nodes. The color scale is shown on the right hand side. The 2D plot, the animated plot, is shown on the right hand side. We'll go back to MATLAB now and we'll vary the grid spacings, time steps, and total time. Let's change the total time from 200 to 1600 seconds and the number of time steps from 2 to 160. Accordingly, our delta t becomes 10 seconds. For accuracy purposes, we still need to reduce the time step even further. Let's change the spatial grids, the total number of spatial grids, from 4 to 15. So the grid spacing in x and y direction is 15 now. We rerun this case. Okay, the initial condition is shown on the left hand side top portion and the final condition is shown on the left hand side bottom portion. The animated view is shown on the right hand side. Since the plate is cooling, the temperature keeps dropping with time. The initial temperature of the plate was 200 degrees Celsius, and with time the temperature keeps dropping all around. At the sides, the temperature is maintained at 200 degrees Celsius. This program is going to run until we hit a total time of 1600 seconds. Looking at the left hand side bottom portion, the temperatures on the interior nodes vary from about 100 degrees Celsius to about 107 degrees Celsius when time equals 1600 seconds. We should be seeing the same results on the right hand side animated plot as well when time is 1600 seconds. We'll now go back to our PowerPoint. To summarize, in this video we presented a 2D transient heat conduction problem. The temperature at each of the 4 sides of the square copper plate is fixed. The initial temperature in the domain is known. We discretized our domain and solved the problem using backward time centered space or BTCS finite difference method. Note that BTCS method is an implicit method and is unconditionally stable. We still need to maintain a smaller time step and diffusion number for accuracy purposes and not stability purposes. We varied the grid spacings and time steps and presented the results graphically using MATLAB. In future videos, we can explore more challenging problems. If you have any questions or comments, please post it. Thanks for watching.